Script theory has probably been the most influential theory of humor of the last 40 years, and the notion of semantic script has been the foundation of the theory since 1985. It has never been universally accepted, but no alternative has replaced it. In a recent paper, I did propose an alternative to scripts. I called it constraints. In this presentation, I will illustrate what is meant by the term. If we assume that our knowledge of the world can be represented as a graph of nodes connected by semantic links, then a script, let's say the script for cat, is the region of the graph that contains the nodes in proximity to the concept cat, perhaps one or a few links away from the node cat. Scripts, though, are more often represented as a slot-filler data container, such as this partial script for doctor. And this is a classic example of a joke in script theory. Is the doctor at home? The patient asked in his bronchial whisper. No, the doctor's young and pretty wife whispered in reply. Come right in. This text is predicted by script theory to be a joke because it meets the following two conditions. One, the first part in green, is compatible with two different scripts, a patient script and a lover script. And two, the two scripts are opposed. As an alternative to the two overlapping scripts, I put forth the notion of constraint, which is also built on the semantic graph, but is not a region of the graph. Let's see an example. If I say that the idea of Oedipus, the Greek tragedy character, takes me to moussaka, the Greek dish, and then I ask where the idea of Don Quixote takes me to, most people will say paella. The semantic graph explains why. We have a node for Oedipus, many other nodes in its proximity, semantic links connecting them, and labels indicating who killed who or who wrote which play, etc. We just need a few of these links to the effect that Oedipus is a character in Greek tragedy is Greek, Greek food is also Greek, and moussaka is Greek food. I like to show the derivation of the destination element as a sequence of operations on the original element as it travels across the graph. So in this case, the value Oedipus changes into Greek tragedy on the first step, then into Greek, and so on until we get to moussaka. Applying the same transformation to Don Quixote takes us to paella. I need to make a clarification here. This transformation could have led equally well to any other Greek dish, like souvlaki, or to any other Spanish dish. So in truth, the destination element is not a single node, but a set of nodes, the set of all Greek dishes, or the set of all Spanish dishes. However, I don't want to use set notation in this presentation. Instead, I will represent these sets as a single value, moussaka or paella. This is an important disclaimer, because the model I am going to present here won't be a complete model, but one that will allow me to keep the presentation brief and to the point. For a complete model, please refer to my published paper. Now we have all we need to add more pairs to the collection, such as King Lear shepherd's pie. And it's also clear that other pairs, like Santorini Maria Callas or Athens paella, do not belong to this collection. Let's define our terminology. These are the inputs, these are the outputs. And the collection, the set of input-output pairs derived in the same way, is what we are going to call a constraint. Let's call this one constraint F. The key idea of this presentation is that this object, this set, constraint F, is not what we normally mean by the term script. Obviously, in the script for Oedipus, there is no slot that has the filler value moussaka. And if we object that this pair belongs to the script Greek, then we'll be forced to admit that the pair Santorini Maria Callas also belongs to the script Greek, but it doesn't belong to constraint F. Furthermore, we won't be able to find the pair Don Quixote paella in the script Greek, and this pair does belong to constraint F. So, mathematically speaking, the set I have called constraint F is not a script, in the sense that it's not, like the script cat, a region of the graph. Rather, a constraint is a multi-step path across the graph that may pass through several scripts. This is the first important difference. I borrowed my second example from Hofstadter, who has analyzed the following riddle. If ABC transforms into ABD, what does PQR transform into? Most pickers, and even ChatGPT, will reply that PQR transforms into PQS. The pattern is pretty evident. We only need the link to the effect that the letter C is followed by D. Based on that, the first step will split ABC into A, B, and C. Then a second step will change C into D. And then the two elements will be strung back together into ABD. Applying the same transformation to PQR will return PQS. So here we have another constraint, the set to which the input-output pairs ABC, ABD, and PQR, PQS belong. And this takes us to an interesting realization. Unlike Oedipus or Musaka, entities such as ABC, ABD, or PQR are not concepts we keep in our long-term memory. And if they are not nodes in the semantic graph, then what are they? Well, all we need in our memory is concepts like P, Q, R, letters of the alphabet, and the concept followed by. The data on PQR is just a composition of these four basic nodes, P followed by Q, all of that followed by R. Inputs of constraints are compositions of more basic concepts. And because we can use recursion in the definition of the inputs, a constraint may take an infinite number of inputs, not only ABC, PQR, and BCD, but why not also ABCD and ABCDE, ABCDEFG, etc. A constraint may then contain an infinite number of input-output pairs. That is, it can be an infinite set. A script, on the contrary, is a region of the graph. It is true that scripts are fractal, that is, every node pointed at is in itself a script, connected to other scripts. But the only way to enlarge a script is to allow a larger number of subslots or chain links in it, and doing that indefinitely would make the script equivalent to the entire semantic graph. So that's the second important difference between scripts and constraints. Constraints can be infinite because they are not regions of the graph, but operations on input sets. And input sets can be defined recursively and thus be infinite. Now let's see how a mechanism of overlapping constraints can model humor, using this example. A man with a hunchback gets lost in a cemetery at night. A ghost spooks him. "What's that on your back?" the ghost asks. "It's a hunch," the man replies. "Can I have it?" the ghost asks. "Sure," and the trade is done. Overjoyed, the man goes to his limping friend and tells him the good news. The limping man goes to the cemetery right away and starts limping about looking for the ghost. The ghost shows up. "What's that on your back?" the ghost asks. Nothing," the man replies. "Here, have this hunchback." Obviously, the trading with the ghost is a constraint in which the input is the situation the characters are in before the trading, and the output is the situation after the trading. So the first input is the datum "the passerby has a hunch and the ghost doesn't keep anything," a composite concept that I'm going to abbreviate as two boxes, one with a hunch, representing the passerby's defect, and an empty box representing the defects kept by the ghost. The constraint we initially evoke, which I'm going to call F, is the operation of the ghost taking the passerby's defect, which is why for this input, the output is an empty box for the passerby and a hunch for the ghost. But there's a second covert constraint that is different from F and yet returns the same output for this input. I'm going to call it F prime. F prime is the operation of the ghost swapping hunches between passersby. For this input, the passerby having a hunch and the ghost having nothing, F prime returns the same output as F. So this input-output pair belongs to both F and F prime. This is a constraint overlap, which we can represent like this. For this input value, the outputs of F and F prime overlap. So the utterances describing the hunchback's trading, on the right, can evoke both the overt constraint F and the covert constraint F prime. They belong to the intersection of the sets of utterances that evoke F and F prime. But for the second input, the passerby having a limp and the ghost keeping a hunch, the outputs of F and F prime diverge. Under F, the passerby is cured of his limp. Under F prime, he's given a hunch on top of his limp because he doesn't have a hunch and the ghost has one for him. We can represent it like this. With the first input, the two constraints overlapped, But when the input switches to the limping man, this is what happens. The utterances describing the limping man's outcome are perceived as incongruities under F, since they can evoke only F prime. And then we realized that the constraint covered the artwork for the first input was F prime, not F. I originally developed this model to account for visual humor, which often requires that the outputs of constraints be non-lexicalized concepts. In a famous scene in The Gold Rush, Charlie Chaplin, stranded in a cabin in the snow and having eaten nothing for days, cooks and eats his shoe as a Thanksgiving dinner. My next example will be a short gag in which he twirls the shoestrings on his fork as if they were spaghetti and then eats them. This gag. In this case, for input visual appearance, the output under F is the visual properties that make a shoestring look like a shoestring. These happen to be the same in part as the output of F prime, which is the visual properties that make shoestrings look like a certain kind of food. They have just the right length, thickness, and flexibility. So the visual stimuli on the right, capable of evoking both F and F prime, coincide. However, when we switch to input handling, the handling of a shoestring as such, which includes untying or tying it, differs drastically from the handling of it as if it were spaghetti, which includes twirling it on a fork and eating it. That's why the switch from the first to the second input reveals the covered constraint F prime. My last example is a joke from the Cold War era used previously by Hofstadter and Gabor. An American says, "Look how free we are in America. Nobody prevents us from parading in front of the White House and yelling, 'Down with Reagan.'" And the Russian replies, "We in Russia are as free as you. Nobody prevents us from parading in front of the Kremlin and yelling, 'Down with Reagan.'" The joke evokes an overt constraint F that outputs parading in front of the White House and yelling, "Down with Reagan" for input America. The derivation is straightforward. We just need the links representing our knowledge that the White House is a government building and Reagan a head of state of America. Constraint F inserts the value White House, then the value Reagan, and finally composites them into parading in front of the White House and yelling, "Down with Reagan." However, there's a covered constraint F prime that returns the same phrase for that input. F prime ignores that Reagan is the head of state of America, and all it does is replace the input value with White House, which it finally composites into parading in front of the White House and yelling, "Down with Reagan," in which Reagan is a constant value appended by the constraint rather than an input-driven value. Clearly, the utterance by the American on the right can evoke both F and F prime as the transformation applied to input America. When we switch to input Russia, the overlap doesn't occur. F returns parading in front of the Kremlin and yelling, "Down with Khrushchev." But F prime ignores that Khrushchev is the head of state of Russia and simply appends Reagan as a constant value at the end of the output phrase, like it did before with input America. Which is why the switch from America to Russia returns an incongruity under F and reveals that the covered constraint F prime was at work. Explaining this joke in terms of scripts is problematic. The lexical field suggests that the two opposed scripts are democracy and dictatorship. And the overlap is that in both political systems, one was allowed to yell, "Down with Reagan." So far, so good. But in both America and Russia, one was also allowed to yell, "Down with Franco," the Spanish dictator, and smoking, and getting divorced. The American could as well have said, "Look how free we are in America. Nobody prevents us from drinking whiskey." And the Russian replied, "Nobody prevents us from drinking vodka." Or the American, "We banned slavery in 1865, and the Russian, "We banned serfdom in 1861, etc." The fact that none of these overlaps results in a joke puts script theory in trouble. Orin reminds us that the falsification of script theory can be accomplished by showing that in the presence of opposed but overlapping scripts, no joke is created. And this occurs regularly, as in a man and his dog went for a walk together, which is compatible with the opposed scripts man and dog. Why then is this not a joke? If a mere coincidence between a democracy and a dictatorship cannot by itself create this joke, its humor must result from the fact that the clause parading in front of the White House and yelling down with Reagan can be derived in two different ways. So perhaps it belongs to two different scripts created on the fly. The script protesting against one's head of state and the script protesting against a particular head of state. An American yelling down with Reagan belongs to both. And a Russian yelling down with Reagan belongs to the second one, but not to the first. But are these two scripts really opposed? The first one is just a special case of the second one. And the only reason why a Russian yelling down with Reagan is not a permissible value in the first one, which is a script created on the fly from the information being communicated, the only reason it forces a switch to the second script is because the first script imposes a restriction on the target of protest based on the citizenship of the protesters. A restriction that has a very large number of input-output pairs if we consider all nationalities and fictional settings, such as subject to the Lion King yelling down with the Lion King. In fact, this is the notion of constraint I have been speaking all along, a correspondence between datasets that transforms the input citizens of X into the output yelling down with the head of state of X. Which is why we can easily recognize the joke's mechanism in any unheard of setting, as in an Earthling saying, "Look how free we are on planet Earth. Nobody prevents us from parading in front of the Imperial Palace and yelling down with Earth's Emperor," and the Martian replying, "Nobody prevents us from parading in front of the Martian Imperial Palace and yelling down with Earth's Emperor." Summarizing, overlapping opposed scripts do not always result in humor, as in a man and his dog went for a walk together. Scripts that do result in humor impose constraints on the possible values of fillers for a potentially infinite set of slots, what I call input data. All jokes are based on overlapping constraints, and overlapping constraints always result in humor, and constraint overlap is readily applicable to non-verbal humor. 3 and 4 are, of course, the main topic of my paper. This is my rationale in favor of considering constraints a better mathematical object with which to model humor than semantic scripts. I have so far skipped the objection that the definition of semantic script is still loose, and it has evolved since they were first postulated. So we could, in principle, extend the notion of script to encompass what I have called constraints, such as the constraints in the Hunchback joke or the America down with Reagan constraint. But even if we allow this, and I don't see the reason for it, scripts and constraints are two different sets. An object can belong to the shaded area, that is, be a script, and not a constraint, such as the scripts cat or democracy. If what produces humor is an overlap of constraints, script theory would still need to be reformulated, so that the first condition for a joke is that the text is compatible with two different scripts of a particular kind, constraints. This shows that the overlapping constraints mechanism is not merely a terminological or notational variant of script theory. How important is this? I have repeatedly asked ChatGPT whether a given text is A, a joke, B, a text that doesn't make sense, or C, a text that makes sense. You may want to pause the video and read this example, or run your own tests on the platform. AI can perform amazingly well in some areas. Recognizing humor is not one of them. And I finish with this because it suggests that modeling the humor phenomenon accurately may be the most important task for humor scholarship, which is perhaps in a privileged position in today's AI debate. It may be that humor has the key to something important about how human intelligence works. A more detailed, complete exposition of this model can be found in my paper. The preprint is freely available on ResearchGate and academia.edu, and I'll be glad to send it to anyone interested. That's my email address. Thank you.